Okay, so the plan has changed slightly. I'm trying to slow down a little bit since I'm seeing there's a homework 5 that is due about 5 days from now. I think you guys are still working on that. So the new tutorial on VGA will be covered today, but the homework assignment is not due until 26. So we do have a lot of time to work on it, almost 2 weeks. That's still reasonable. Because we have homework 5 and homework 6, so including lab 5, right? It's about 3 assignments in about 2 weeks. So I just decided to cancel the lab next week. It's basically making the lab 5 a 2 week lab. So there won't be a lecture on Tuesday. If I cover a new tutorial, there will be a new assignment. So instead, I probably will just give time to you guys to either prepare for the midterm exam. You can look at the code that we have been doing in the quizzes and homework assignments and try to be familiar with all the pattern in the code. So be prepared for the midterm on Thursday next week. So there's no lecture, no lab on Tuesday next week. Okay. And after that, it's still a little bit too intense. I'll probably just cover one lecture a week to make it slightly more reasonable. Any questions on this? No, you're good. Okay, so the VGA experiment is really fun. The only thing is, it's a little bit old technology. But other than that, it's a really fun experiment. Even though it's not being used on the laptop anymore, but it's still used for monitors and projectors. Still useful, at least for another 5 years or so. So there's a tutorial on it and also a lab with it, just with more experiments. So I'll give you an overview on the VGA protocol really quick, and it's really simple. If you look at the code, and that's a VGA controller, and that's the top. Okay, you don't expect too many other things, and the basic idea is for the VGA protocol. Some of the standard parameters will be probably on the quiz in the future. But keep in mind that the ones we are using is the 640 by 480. Keep in mind, 640 by 480 as a pixel array. If you search on IEEE standard, you'll see there are different types of VGA resolutions, and the most popular one is the 640 by 480. You can see if you are using this resolution, as a digital design engineer in the company, you need to know the frame rate, the pixel frequency, and the frame resolution, and also the picture frequency. So what are the differences? So this one is the frequency of assigning every single pixel. So that means it's assigning 25.175 million pixels per second. 25 million pixels per second. What does that mean? I mean, this is HDMI, but I believe that's a VGA. So you can zoom in, you can see pixels, right? It's about 25 million pixels per second. Okay, and depending on how many pixels you have for one picture, and then you will have a refresh frequency, which is over here. Okay, let's take a look at it if that makes sense. I'm running out of cables, but I will give you one cable. This is not due until 2 weeks from now. Okay, so you don't have a cable, right? 1, 2, 3. You don't have a cable.
No.
So first, use your calculator in your computer. Probably do a multiplication. 640 by 480. What is that number is? Let's do it here probably together. 640 by 480. How many pixels?
30,000.
About 30,000 pixels, right?
Missing a zero.
Missing a zero. Oh, okay. This many pixels. Okay, this many pixels, and it's assigning about this many pixels per second. So how many? How do you do the math? How long it takes to finish? 2 seconds? About 2 seconds, roughly. I don't think so.
No, actually less than a second.
So this is the number of pixels, the count, right? And this is this many counts per second.
Is it the frame rate of the monitor?
So use this one divided by 25175,103,123. Right? This is how long it takes to finish all the pixels. Is that correct? Right? You have the number of pixels, and this is how long it takes for finish it per second. And this is how many seconds it takes. It's about 0.012 seconds. So what's the frequency? I mean 1 over that number, right? So 83 hertz. Are we getting the point here?
Yeah.
Yeah?
Yeah.
Everyone? So that means for a 640 by 480 picture, this many pixels, it takes about 0.012 seconds to finish the assignment of the pixels for that picture, and which is probably giving you 83 hertz. Did you see the same issue with other faculty members? Other lectures?
I don't have other lectures in this.
Okay, I saw the same thing. So just yesterday, that was the department meeting. I saw the exact same thing in that classroom over there, 750. It's probably not my laptop's issue. I don't know.
Yeah, we had the same issue in practical robotics. It was just after this in this classroom.
Same thing, right? Yeah. Did he use a HDMI or
Yeah, I
just?
think he used an HDMI.
Okay. Yeah, I think the HDMI is the issue. When I used VGA a few years ago, I've never seen this problem at all. So we should switch back to VGA. You can see the pins of the VGA core if you take a look at it. All these like metal rods, right? Super big metal pins. It's really reliable. Doesn't like all these little pins are being printed on the film of the HDMI or any of the USB cords. The lifespan is really short. Probably if you use it daily, probably every like 1 or 2 years have to replace it, the USB cords. Yeah. Do you see that? It's so strong, right?
Yeah.
That's why it's so reliable, and it's analog. It is analog. We'll take a look at it. It's really interesting technology. Right. So.
Actually, why did they switch away from VGA to HDMI? Is it just because like you fit more pins on HDMI?
Oh, it's just bigger. VGA is too big.
Too big.
Yeah, it'll make it more compatible. And also HDMI is able to transmit audio signal as well, but VGA is just the pictures, no audio. Right. But this doesn't match, right? You see this is like 83 hertz, but seems like it's 60 hertz instead. Refresh rate. So 640 by 480 is giving like 60 hertz instead of 83 hertz. What's the problem?
Is it a mismatch?
No,
Going
it's because 640 by 480 is the pixels of the picture, okay, the pixel of the picture, but the VGA standard protocol for this 640 by 480 standard, it requires some redundant time to be spent in order to have a very stable picture assignment or solid colors. So that one these are not pixels, but these are time. Take a look at it. So eventually it's actually giving you 800 by 525. It's just numbers you have to know. These are just standard. We're not calculating anything. Okay. So for the standard 640 by 480 pixel resolution, it requires 800 by 525 of scanning. So it takes time to assign the pixels of the 640 by 480. But the thing is, for the rest, these are just time. There's no pixel to assign to anything. And if you look at the protocol, and if you look at the explanation, what's really happening is it's trying to align that electron gone of the CRT, whatever technology, but it's not CRTs. These are all LCD or LEDs. So it's just probably waiting for electron. There's no electron gone as well for the monitors, for the modern monitors, right? So it's probably just waiting for something to make it stable for the older monitors, but for the modern monitor, we don't have the problem. But still have to follow that protocol. So eventually, what's really going on is, if you look at this one, it's got front porch and back porch. Okay, and there's a synchronized signal as well. So all these ones take time. So the x-axis is time, but these are not real pixels. So what's really happening is it's doing 25 megahertz of the pixel assignment for the real picture, like this part, the real colorful part. It's doing boom, 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 right? So it's actually assigning from left to right. If you look at the monitor, it's from the top, left to right. So finish the first line first, and then switch to the second line and do it point by point. It's able to do it really quickly at 25 megahertz. So if you just use your naked eye, you are not able to resolve it. But the thing is, if you use a high-speed camera, that is able to see the refreshing of the pictures. Okay, that's why if you use a camera, it's seeing like scanning from top to bottom, right? But the thing is, for every roll scanning, if you look at this part, horizontal display area and vertical display area, it's from if you're doing vertically, it's the same thing. So vertically, whenever it finishes the pictures pixels, it has to wait for this period of time to finish the whole vertical scanning. And these are called front porch and back porch, before and after this sync signal. So the sync signal is telling the controller that it just finishes that vertical scanning, so it's ready to move to the next column. And for the horizontal scanning, it's the same thing. So whenever it reaches a sync, it's telling the controller that it just finishes that line, so it's ready to switch to the next line. But however, it requires a front porch and back porch. These are just a time. There's no pixels, keep in mind. But the thing is still doing the same frequency, which is 25 megahertz. So if you count how many pixels, again, it's not pixels, because there's no pixels to assign to the monitor. It's just time, but still using the same frequency, which is 25 megahertz. It's still using the number of pixels over here. If you look at the protocol, so for example, front porch has 16 pixels. Keep in mind, there's no pixels. It's a 16 pixel time. It's 1/25 megahertz per pixel. So 16 pixels will take 16/25 mega seconds to finish. So you have to program that into a Verilog. If you just follow the protocol, to program the hardware, you can finish that pixel assignment using Verilog easily. If you look at the code, it's already given. Okay, so here's the Verilog code for the VGA controller, and there's the top. This is the top. Super simple. If you look at the hardware, so VGA controller, for our assignment, for our design, we are using a ROM using ROM to store the image data. So it's programmed it's into our IPGA board. So in that case, your VGA controller is also in the IPGA. It's also inside the IPGA. So in that case, you have two digital blocks inside the IPGA, right? One is the VGA controller, one is the ROM. So the ROM stores the picture, the data of the picture, the pixel data in it. And then you assign address, give an address, so the ROM is able to take in that address like a decoder. You give an input, which is the address, it's going to output the pixel data line by line. So every row has a pixel data. It's 8-bit pixel data. You can see it's from 7 to 0. It's byte by byte, every single row. Okay, and that ROM data is given. So it's a picture data is given. You assign the address, and the data, 8-bit data, will be available at the port. It's very simple. So ROM is really simple. Okay, you assign an address, and the data at the address will be available at the port. It's ready. So if you design a VGA controller, right, you are throwing the address to it, and you can expect 8-bit data is available for your VGA controller. You can directly take it in, right? You take it in, and then do something. Okay, you can look at the Verilog code, what we did over there, and give it and directly assign it to all these VGA ports. So that's the interesting part of this technology. Okay, if you look at the code or the constraint file, probably. Let's open up the constraint file. You can find one. Constraint. This guy. Here. VGA connector, okay? So the VGA port is the hardware on the board. And you can see there's a VGA port on it. So accordingly, we have definitely the IPGA has pins that are physically connected to the VGA port. That makes sense. If you look at it, definitely the first step to uncomment it. Important. All right, uncomment it. And then you can see for VGA red, you have 0, 1, 2, 3. 4 bits. 4 bits for red. So it's going to be 4 bits to resolve the red color. The red color. But you are wondering, why do we need the 4 bits to resolve it? Sometimes the bright red, sometimes the dim red. Okay, so the red has intensity, right? So if you have a super strong red and you mix with other colors, it turns into a different color. So you want to resolve that, the whole red color, using different intensities or brightness of the red color. And you are using 4 bits to resolve it in theory, okay? So you do have 4 bits to resolve it on the IPGA. But eventually we are only having 8 bits in total. Keep in mind. 8 bits in total. You have 3 different colors, right? 3 times 4 becomes 12. So you do have 12 bits to resolve all the 3 colors R and G and B. But the thing is, we are not using all the 12 colors, all the 12 bits. We only use 8 bits to resolve the colors in the picture, which will result in what? A poor quality of the picture. So if you look at your IPG board, it has a super bright blue color on it, right? It's beautiful. If you look at the ones that I'm able to display on it, the color is getting sort of distorted. See? Showing like a green, bluish, and the resolution is poor. That is because we do have 12 bits, but to make it simple, we're only using 8 bits to resolve it. So we're dropping like 1 bit for 2 colors and 2 bits for another color. So totally we dropped 4 bits to reduce it from 12 to 8. So you'll be able to see that later. Don't worry about that for now. And one more question here. So eventually, if you look at the hardware pinout, okay, hardware pinout, it labels the number, the pin numbers from 1 to 15. From 1 to 15. So you'll notice pin 1, pin 2, pin 3, pin 5, so on and so forth. Okay? And if you look at the functionality of the pins, it's being put in the table. So which ones are really the video data pins? Which ones?
1, 2, and 3.
1, 2, 3. So does that pin, are these pins like fancy pins and you can have a boss on it, or just a one metal rod?
Just a broad.
If you look at the pin, it's just one piece of metal. So how many bits on that metal? Just one bit, just one voltage node. So you're wondering, how do we do that? Like one metal rod can do like 4 bits.
Is it just like pulse it and then have like something to
That's serial, right?
Yeah.
That's HDMI probably, or something else. For this technology, it's not. So how that works? Look at this. So what's happening?
Looks like
Is that familiar to you guys? That is why a lot of times you should know that superposition is one of the most important theory you have learned in circuits. A lot of people don't even have assignment in the Circuit 1 class for that theory. It's most often used. You see, the inside the controller, before it's being delivered to the VGA port, what's happening here? So if it's 4 bits, right? If it's 4 bits, and we know that the MSB takes more weight. So the MSB of the 4-bit data must wait for a higher analog voltage. And this is the superposition theory here. You can see you have 4K and divided by 2, divided by 2, divided by 2. Okay? So in that case, if you apply superposition, could you let me know which one will give you higher voltage? If you only apply that voltage pin to it, which one will give you a higher, contribute higher voltage to the VL, which is the final output here? So that's inside the controller, right? The inside control, the controller will give you 4 different digital lines, which makes sense, right? Since we see that there are 4 digital lines for each color, okay? And definitely can tell this is R3, R2, R1, R0, which means this seems to be the MSB. MSB. This is LSB. Okay?
yeah.
Then why this MSB is contributing a higher voltage to this guy, has higher weight?
Because the lower resistance.
Why? Then why? Remember how do we do superposition? Alright. So think about that. If you took, how many of you are in my no VLSI? So you are not. Everyone else actually, right? So superposition, you got. Just imagine there's a power source, voltage source. Okay, I got a voltage source V1, V2, V3, V4, okay, connected to these ports. And then the very first step of the superposition is what?
Cancel out the other ones.
It cancels the other ones. Cancel or do what? What else?
Short.
Short where? Yes. So, for example, V1 only. Okay. So V1 only, then V2, V3, V4 need to be shorted to grounds. Make sense? Okay. So these are grounded. Okay, these are grounded. So V1 only. Okay. Then, if you look at the whole circuit, all these are grounded, which means they are in parallel and grounded. And these are higher resistance. So eventually it results in a bigger resistor here, okay, and a small resistor here, right? So in that case, V1 in the circuit, including the VL over here, is like a voltage divider circuit, and most of the voltage is being dropped here or here.
On the second.
Which one?
On the second one.
On the second one, why?
Because
So VL, how do you look at VL? So VL will be the voltage dropped from here to ground.
yeah.
And because these are grounded,
Mm-hmm.
so VL will be the voltage across these two terminals, right? Okay? And since this is a V in, one resistor, two resistor, so this will be the voltage divider, and this one drops most of the voltage. So that is why this is having higher voltage, because of the resistor here is bigger. Right?
Yeah.
So if you replace it using this one, now V1 is grounded, V2 only. So which means these three lines are grounded. These three lines are grounded. And because this one is dropping more voltage compared to this guy. And if you combine 1, 2, 3 resistors, but at least if you have, for example, this, and this in parallel, and do you know can you have an estimate about the parallel resistance or no? It'll be what? Don't give them the exact number, but it will be less than what?
Less than 1. Right now it'd be less than.
You got 3 parallel resistors, right?
Yeah. It'd be
Very important. Let me
But-
tell you, okay? 100, 1K, 2K. So what's the overall parallel resistance will be?
it'd be,
100, 1K, 2K in parallel. It will be what?
it'd be less than 100, right?
It will be less than 100.
Yeah.
Make sense?
Mm-hmm.
It will less than the smallest resistor. So in that case, if you have this in parallel, it will be less than what?
Less than 500.
Yeah, will be less than 500. Will be probably less than 500, probably like 300 something ohms. So in that case, if you have V2 only, most of the voltage will be dropped where? At the 300 ohms or the 1K ohms?
The 1.
The 1K ohms. Is the 1K ohm voltage BVL or no? Is the voltage across the 1K ohm resistor a VL? No. But the 300 ohm resistor will be VL because VL is over here. VL to ground, okay? So that is why the voltage being dropped across the 300 ohm resistor instead of the 1K. So definitely this one will give you a less weight. Okay, if you put a 1 here, your output voltage will be less than if you put a 1 here. Make sense? So definitely the MSB has more weight compared to this bit, and so on and so forth. So this one has the least because this resistor is so big, it's going to drop most of the voltage and then leave a little bit, only a little over here, which is, still 300 ohms. So this contributes the least. So in that case, eventually, because there's only one rod, right? One rod for each peak, for each signal line. So eventually, it's giving you a analog signal at each rod. So the VGA port is digital before the rod, but eventually when it arrives at the rod, it's an analog signal. So you can treat this guy as a little what?
It's the voltage source. Or it's like
Or
a modulating voltage source.
yeah, it's basically a DAC.
Yeah.
Okay? It's not an R2R DAC, but it's a DAC. It's a DAC. Digital to analog converter. Really poor quality or resolution DAC. Right? It's a DAC. So these ones are easy because these are just one signal line. There's just one signal line. It's a sync signal. Vertical sync, horizontal sync. When and where we need a sync, if you look at the code, you can definitely tell. I think.
It's basically the clock is on, like the syncs, because they're basically keeping the signals that keep them synchronized with the monitor. From
Yes.
the-
Similar. Yep. Exactly. The SX and SY over here is the size of the pixel, the size of the picture. And you can see we assigned 80 by 80 because we know that this picture is 80 by 80. So we just adding a new layer into it. But the thing is, if it's not a specific 80 by 80 picture, you don't need SY and XX to set up the limit for X and Y. And since we still have time, I'll let you guys, it's not due until 2 weeks from now. So you do have time to go through the if statements and see if that makes sense. And so the diagram is over here for our connections.
What is clock 25?
It's 25 megahertz, right? So 25 megahertz, so we are using a, do you know how we calculate it? Why is 25 megahertz? It's given, that's right, it's for the protocol, right? So for this 64 by 480 protocol, it's 60 hertz. It's calculated by this number because including the front porch, back porch, and the sync signals time. So it's, even though it's only 6040 by 480, but actually it's taking 800 pixel time for horizontal scanning and 525 pixel time for vertical scanning. So eventually you are getting 800 by 525 total number of pixel time. And you know that the frequency is 25 mega. So do this math, and eventually it's giving you 59.99 hertz. And that is why for this standard, it's scanning the picture, the whole picture, at 60 hertz. So the screen refresh rate is 60 hertz. That's how we calculate it. So in the quiz, if I give you a different picture size, okay, and the frequency, are you able to calculate the refresh rate?
Yeah.
Okay. And you can see here, for the same protocol, for the same standard, 6040 by 480, still, okay, and it's given how number of pixel time for front porch, sync, back porch. It's given, okay, you just have to follow it. 16, 96, and 48. So that takes how many clock cycles? You just have to count it into your scanning, okay? And eventually, in total, it's giving you 800 for horizontal timing. And for vertical timing, it's very similar, right? After you finish the 480 by the 480 pixels, you still have to, adding the time of front porch, sync pulse, and back porch as well. So look at here. So for the coding part, there are several names of variables. You can see this is horizontal display, I think, H display, and horizontal front porch, FP. So that's from here to here. And this is horizontal display plus the front porch plus the pulse width. So the pulse width is like 96 for horizontal and 2 for vertical, I think. See? It's 96 pixel time for horizontal and only 2 pixel time for vertical. So for the controller programming, it's just a bunch of if statements. So it's taking a look at the current counts. If it's reaching that limit of the horizontal pixel numbers or not, if it's reaching, move to the next, right? Move to the next line. And also for the vertical as well. If it's reaching the bottom and reaching the horizontal limit, you know that the whole picture scan is done. So you start from the very beginning, start a new picture. So these are what all the if statements, the nested if statements are doing. So you can look into the details over here. It's not doing anything else, but this like counting and looking at the number of counts at the picture. The 25 megahertz clock is definitely from the 100 megahertz clock. That's the fastest clock you have on the board. We are not programming the 25 megahertz clock ourselves, so there's an IP block that you can directly use from the Vivado design environment. And you can just let it know what kind of frequency output you need, and eventually it's going to generate the IP. It's like a module, and you can use the module, instantiate that module in your top. So the way that works is like this, very simple. Here's the IP you created using the GUI, the graphic user interface. It's going to directly just follow all the steps and put in the parameters in. Eventually it's going to generate a module for you. And the name of the module is called clock wizard _0 is number 0. And you name it as clock. You can name it whatever you want. You name it as clock. And it follows a certain order. If you open up this clock module, you can see it has the clock output at the first declared input, declared port, and then it declares the input clock. So it just follows a certain order, so you don't have to use the dot something statement. So it's going to directly make the connections with the ports being declared in the sub module. Does it make sense?
Yeah.
So these two, so you can see clock 25, it has to be the output, right? And clock is the input. So within the sub module, it's also declaring output first and then input. So they're aligned. But you can also use a dot statement to make the connections. It's going to do the same job. So these are the instructions about how to create that 25 megahertz clock module. As you can see, here's a little module. It's a clock divider, and output is 25 megahertz. And just make sure you follow this. Eventually, it's gonna turn on a clock module like this in your design sources. So if you're curious about inside structure of it, you can see that's why I did that, because I want to know which one is being declared first. So I open it up and it shows me output first. So I know that I should connect the output to the instance first. A memory, I think we already did it in the data storage tutorial. Just follow, okay? It's creating a ROM, and the sync image file is over here. So this image file is this basic 3 boards image. So you load it, and eventually it's going to generate a ROM. It's also one of the design sources over here is a ROM, and that ROM holds the data. It's a read-only memory, so it holds the image data in it. It's being used as a Verilog module here. How that works, Vivado did it for us. So you load the image data, so this is pixel data in it, and Vivado will directly generate a ROM, which is a Verilog module with that data file in it. So you can directly instantiate it in your top. Okay? So the ROM has an address input and has a data output, but nothing else. So the data output is 8 bits and address input is 13 bits. Okay, you give a address input, the image data output will directly available at the output over here. So you can directly use it in your top. So after the task 2 is basically just repeating. Okay, there's nothing new for it. After we are able to show this one on the monitor, and the task 3 is asking you to display solid colors on the monitor and blink it. So see if you understand what's really going on in the code, in the Verilog code. If you understand it, you modify it and show different colors, just pure RGBs, and blink it every second. Make sense? I think that's these are all the 3 tasks for you guys, and this is due on 26. And some of you came in a bit late, so I just told you guys that we're not having a lecture on Tuesday next week. We're not having a lab as well on Tuesday. So to give you some time to work on assignments, including homework 5 and homework 6. And there's a midterm exam on Thursday next week. So from Tuesday, the week after, we'll have a new tutorial. So this LCD circuit basics and protocols, all the timing logic is for the lab on that day. So we will have a lab on 25th, but there's no lab next week. Okay, and so Thursday, the week after, we'll start our soft core. This is really exciting because we are basically making a microcontroller on IPGA. It's a soft core. It's not a hard core. So the difference is we use Verilog to program all the lookup tables and logic gates to make a CPU in it or microcontroller in it. So that little microcontroller is developed by one of the engineers in Xilinx. I think it's just for educators and students in college. It's not a commercial core, but we can still do a lot of things, including program assembly and load the code into it, so the instruction pointer is able to take out every single instruction each time and eventually put in a CPU for computation. And we didn't have a very complicated tasks for the microcontroller. Didn't want to challenge the microcontroller a lot. But I believe there's a interrupt module, so we can have some fun with it, I believe. So I'm gonna work on it a little bit and eventually develop some new tasks and or modules in the lab for you guys to play with. But the current one we have is really very fun. Okay.
Actually, wait. If you're programming the CPU, does that mean you can actually change the specifications that it runs at?
What do you mean by specification? The CPU specification? Yes,
Yeah.
you can definitely modify the Verilog code to change the CPU, to change the core.
Mm. Okay.
It's totally customizable. Everything's under control. It doesn't like the Arduino microcontrollers. You have to use whatever existing on the hardware and looking at the data sheet, right?
Yeah.
So this time you guys are creating the data sheet. Whatever, everything's customizable. If you want to add a 64-bit bus in it, you can directly do it. And that is why a lot of times IPGAs are faster than the microcontrollers. So first, because IPGAs are usually using smaller technologies. For example, our IPGA, even though it's already almost like 8-year-old technology on the IPGA, I think it's A7 Arctic 7 IPGA chip, but it's under 28 nanometer technology. 28. But Arduinos are 350. It's almost the C5 we are using in the VSI class. Okay, so definitely that is one of the reasons why the Arduinos are running at 16 megahertz, right? Arduinos, but however this one is 100 mega easily. Another reason is when you purchase a microcontroller, everything's already designed inside because they have to accommodate other different modules to make it more versatile, I think. So people can use ADCs and display modules and all different kind of functional blocks on the microcontroller to do all different kind of things. So probably have to compromise the speed of the core for certain tasks. So that is why it's not called ASIC. It's not application specific IC. So it's a general purpose microcontroller. However, when you are doing IC design in digital VLSI It's called ASIC because it can be application-specific IC. For example, the CPUs in iPhones or in your Samsung phones, all these CPUs, these are totally customized ICs or ASICs, and it can, for example, have all the display pins on the right hand side or close to each other, and all the memory pins on the other side, in order to make the phone more compact. Okay, all these kind of design ideas you can implement onto the ASIC. Like IPGAs, for example, you are working for a defense contract or for NASA in the future, and there's a scientific instrument that requires an IPGA chip having 64 output pins in parallel, right, on the chip and on the right hand side. There's no microcontroller can do it. So the only way, the two methods you can do that is, first you can use IPGAs, because all the pins on IPGAs are you can all totally assign them to different purposes. They are all free pins. You can assign like 64, even 128 pins on one direction, or you can do totally ASICs like VLSIs, but which cost a lot of money, usually $1 million for one design. It's very difficult. If it's just very small contract, it's probably IPGAs will be the best option. And a lot of times, you can purchase the high, more advanced IPGAs from Xilinx or Ultra or Intel right now, which has hard cores in it, like ARM cores or other different cores in it. So it doesn't like a soft core you are going to program, which will probably have more time delay and but more flexibility. But there are a lot of other issues as well. So there could be a hard core in it, and it can directly design the peripherals, the digital blocks, and make the connection to the hard core, and then use it for a specific application. So that is why IPGA is so popular. It is also ASIC, right? ASIC. It's just a little bit more expensive than the totally customized integrated circuits. If you're only using like 10 or 20, if you're trying to sell like 100 million, so definitely ASICs, the digital ICs will be more profitable. Okay, so I will let you guys work on the VGA code yourself, because going through every single line in the code will make you super sleepy. It doesn't make sense, to read the code. People get lost after the fifth line, usually. So you read it and try to understand yourself. It's super easy, and play with it. Okay. Any questions on this? No. And I'll let you guys go earlier. And for the people who don't have a VGA core, I think I'll be able to give you. Let's see, no lecture Tuesday. Maybe during office hours on Monday or Friday, I'll make the course available in my office.